Given two functions f and g, we discussed the differentiability of f plus g, f minus g, f into g and f by g before. Now we are going to discuss the differentiability of f composed with g. Remember, we saw while learning continuity that if f and g are continuous, then f composed with g is also continuous. So what we are going to learn now is kind of analogous to that result for continuity. This result is called the chain rule. Let us first go through the setup for the result. So what we have is we have two functions, f from j to r, g from I to r, and we are given that f of j is contained inside I. Because f of j is contained inside I, we can define g composed with f. Why? Because if you take f of x for some point x, then f of x lies inside the domain of g, as f of j is contained inside I. So we can talk about g of f. So g of f is a function from j to r. Further, if we are given that f is differentiable at c and g is differentiable at f of c, then g of f is differentiable at c. Moreover, g composed with f, the derivative of that at c is equal to the derivative of g at f of c into the derivative of f at c. So it's not just differentiable, we can also explicitly calculate the derivative using this formula. Let us now look at the proof of this result. The basic idea for the proof is quite simple. We will construct two auxiliary functions phi and psi such that phi is continuous at c if and only if f is differentiable at c. Psi is continuous at f of c if and only if g is differentiable at f of c. We will then construct another function which is expressed in terms of phi, psi and f, and that will be continuous because of the continuity of these three functions. And the continuity of this new constructed function will imply the differentiability of g composed with f at c. That is the basic idea of the proof of this result. Now that we have the basic idea, let us flesh out the details. Let us define the two functions phi and psi. So the function phi of x is given as f of x minus f of c by x minus c if x is not equal to c and is equal to f dash of c if x is equal to c. Clearly, the function phi is continuous at the point c because limit extends to c, f of x minus f of c by x minus c is equal to f dash of c, and that is the value at x equal to c. Hence, the function phi of x is continuous at x equal to c. Let us now similarly define a function psi of y. Psi of y I define as g of y minus g of f of c divided by y minus f of c if y is not equal to f of c, and is equal to g dash at f of c if y is equal to f of c. Again, from the differentiability of g at f of c, we get that this function psi is continuous. Notice that g of f of x minus g of f of c is equal to psi of f of x into f of x minus f of c. Correct? Just from the definition of psi. From that, this clearly follows. But now, notice that we can write this as psi of f of x. I'm keeping psi of f of x as it is. But f of x minus f of c is equal to phi of x into x minus c. Correct? That follows from the definition of phi of x, which can be rewritten as g of f of x minus g of f of c divided by x minus c is equal to psi of f of x into phi of x. Let us now look at the right hand side of this equation. Limit x tends to c, phi of x exists because phi is continuous at c. So limit x tends to c, phi of x is equal to f dash of c. Similarly, limit x tends to c, f of x exists. Limit x tends to f of c, psi of x will also exist. So because of that, by the theorem that we proved for continuity, limit x tends to c of psi composed with f of x will also exist. And because of this, limit x tends to c of this entire thing will exist. So if limit x tends to c of the right hand side exists, limit x tends to c of the left hand side also has to exist. Correct? Hence we can take limit x tends to c this. So this limit exists because the limit on the right hand side exists. Understand? So hence I can take limit x tends to c here. But if we take limit x tends to c of this quantity, what do I get? By limit of product is equal to product of limit, I get that this is equal to limit x tends to c of psi of f of x into limit x tends to c of phi of x. Now this is equal to psi of f of c. How do we know this? We know this from the continuity of f at c and psi at f of c. And this is equal to limit x tends to c phi of x is equal to phi of c. But what is this? What is psi of f of c? Psi of f of c is nothing but g dash at f of c. And phi of c is nothing but f dash at c. And hence, we get that the derivative of g at f of c exists and is equal to this quantity, which was the result we wanted to prove. Let us now see one application of the chain rule. So let me just write the setup. So suppose we have a function f from I to r, and say let's say f of I is equal to j, and g is a function from j to r such that g composed with f of x is equal to x. That means g is equal to f inverse. Now from the definition of g of f, it's clear that g composed with f dash at any point c is equal to 1, irrespective of the point c. Because we know that the derivative of the function x is equal to 1 at all points. Now suppose that f is differentiable at c. F dash of c is not equal to 0 and g is differentiable at f of c. So by chain rule, what do we get? We get that g composed with f dash of c is equal to g dash at f of c into f dash at c. But we saw that this quantity is equal to 1. That's something we saw earlier, right? Here. So because of this, we get that g dash of c into f dash of c is equal to 1. which will imply that g dash of f of c is equal to 1 by f dash of c. So if g is differentiable at f of c, we know what the derivative of g at f of c would be. And this is also helpful in proving that the derivative of g will exist. Why? Because we have noticed that often to prove that a limit exists, we need to guess the possible limit first. And here we already have that guess ready made for us. So that is the advantage of this result.